Good afternoon, ladies and gentlemen. My name is Matvii Tovstenko-Zabelin, and I'm a PhD student at the Institute of Macromolecular Chemistry of the National Academy of Sciences of Ukraine. Today I will present our work on temperature sensitivity of grafted xanthan poly-N-isopropylacrylamide hybrid nanoparticles in aqueous solutions. Our main goal was to synthesize and investigate new polymer hybrids that combine the nanogel micelle-like structure of xanthan coils with the thermoresponsive properties of poly-N-isopropylacrylamide, or PNI-PAM for short. By doing so, we aim to create smart materials with potential applications in drug delivery and biosensing. The focus will be on the synthesis and properties of these hybrids, but I will start with some brief background on xanthan coil structure, which is key to understanding the approach we used. This part serves as a short reminder of our earlier findings on xanthan coil structure. Traditionally, the coil conformation of xanthan in solution was considered to be a statistical coil without internal order. However, in our previous work, based on TEM micrographs, dynamic light scattering, zeta potential measurements, and several more methods, we proposed a different micelle-like model. In this model, the xanthan main chain behaves as a flexible backbone that folds tightly to form a hydrophobic core stabilized by hydrogen bonds, while the charged side branches extend outward into the solution. This organized arrangement is important for the present study, since charged carboxyl and carboxylate groups on the outer surface enhance the absorption of the redox initiator and allow the creating of hybrid nanoparticles with a distinct core shell morphology. Now moving on to the synthesis of our xanthan PNI-PAM hybrid nanoparticles. We used a grafting-from approach via radical polymerization to graft poly-N-isopropylacrylamide chains directly onto xanthan macrocoils. The schematic here shows the overall synthetic route, starting from xanthan micelle-like structure through activation of hydroxyl groups with cerium redox initiator to grafting. What's more, we showed via TEM that xanthan macromolecule keeps its coil conformation after adding the initiator. Therefore, it can be stated that grafting occurring from the surface of the xanthan micelle. The table shows two basic parameters of the obtained hybrid: the hybrid weight and the grafting degree. To verify the successful grafting and to study the structure of our hybrid in the bulk state, we used a combination of analytical techniques: FTIR spectroscopy, dynamic thermogravimetric analysis, and differential scanning colorimetry. Each of these methods provided complementary information about chemical structure, thermal stability, and phase transitions in our material in a bulk state. Here you can see the FTIR spectra of pure xanthan and the xanthan PNI-PAM hybrid. In the hybrid spectrum, we observe new vibration bands corresponding to PNI-PAM secondary amide groups, as well as clear shifts in existing xanthan bands. The arrows mark bands associated with two types of hydrogen bonds, corresponding to structures of two types, formed by NiPM units in the PNI-PAM shell. This slide presents the DTGA curves for both xanthan and the hybrid, along with two tables summarizing key findings. The upper table compares the water content in the two samples, distinguishing between absorbed water and immobilized water. It was found that in the bulk state, the hybrid contained a noticeable amount of immobilized water, about 10.4% by mass, as well as around 2.4% of absorbed water. Both values are slightly higher than those of pure xanthan, reflecting the stronger water binding ability of the hybrid material. The second table highlights an interesting exothermic process that occurred before the onset of decomposition. We interpret this as a colloidal crystallization event. caused by the ordering and densification of colloidal particles. Here you can see a comparison between the xanthans and hybrid stability to thermal oxidative degradation. As we can see, 3 stages with exclusively exothermic effects take place in process of xanthan degradation, and only 2 degradation stages for the hybrid. There's clearly visible that the first and the main stage of the process start at 60° higher temperature in case of hybrid compared to xanthan. Therefore, it could be stated that our hybrid shows more of a thermal stability. The mass of non-decomposed residue in the end of hybrid's decomposition appeared to be several times smaller compared to xanthan. Noticeable thing is that the first stage of hybrid decomposition showed 2 substages with different thermal effects. Endothermal at first, then exothermal. We assumed that the endo effect corresponds to the chemical reactions without oxygen participation, and the exo effect to the chemical processes after oxygen binding. This slide shows the DSC curves of xanthan and the hybrid in the bulk state. 2 new thermal transitions were detected in the hybrid, which are absent in the individual components. The first, in the low temperature region, around -100 to -80 Celsius, is similar to a transition observed in proteins and is attributed to increased atomic mobility due to the onset of anharmonic motion. The second, in the high temperature region of about 192 to 200 Celsius, appears after complete water release and is accompanied by a positive thermal effect. We interpret this as colloidal crystallization of nanoparticles caused by densification of the PNI-PAM structural layer. In the bulk state, the hybrid displayed an amorphous micro and nanophase structure that retained features of both individual components. This was evident from the appearance of 2 distinct glass transitions on the DSC curve, one at about 5.2 Celsius corresponding to xanthan, and another at around 134.8 Celsius corresponding to PNI-PAM. The coexistence of these transitions indicates that the hybrid contains separate micro and nano domains characteristic of each component, rather than forming a completely homogeneous phase. In this part, we will consider the main physicochemical properties of our hybrids in aqueous media, including their concentration and temperature-dependent viscosity, particle size and surface charge, as well as the nature of interparticle interactions. From viscometric measurements of 2 series of solutions at different concentration, we determined the intrinsic viscosities and Huggins constants for both xanthan and the hybrid. Xanthan showed the typical polyelectrolyte behavior, while the hybrid did not. The intrinsic viscosity of the hybrid was found to be much lower than that of xanthan. It is also notable that water behaves as a good solvent for xanthan and as even better solvent for the hybrid. Temperature-dependent viscometric studies revealed a sharp step-like drop in reduced viscosity of the hybrid solutions around 34-35 Celsius, in contrast to the almost constant behavior of pure xanthan. The effect was strongly concentration-dependent. In dilute solution, the viscosity decreased about 9-fold at the transition and remained stable upon further heating, with reversible behavior upon cooling. In more concentrated solution, the viscosity drop was followed by gel formation. The solution turned into an immobile white gel, which regained fluidity upon cooling through the same transition point. This difference reflects the shift from intraparticle hydrophobic compaction at low concentration to interparticle hydrophobic association at high concentration. Dynamic light scattering confirmed these observations, showing a very sharp increase in the Z-average diameter of particles near 33.5 Celsius, apparently due to their strong aggregation, which was in good agreement with the viscometric data. Dynamic light scattering of xanthan PNI-PAM hybrid solutions at 25 Celsius and a concentration of 1.67 kilograms per cubic meter revealed a three-model size distribution. The smallest mode corresponds to individual nanoparticles, while the two larger modes represent aggregates of different sizes. Despite their high aggregation tendency, most of the volume fraction, more than 80%, was still made up of individual hybrid particles with an average diameter of about 28 nanometers. Compared to pure xanthan nanogels, which has an average size of 35 nanometers, this indicates that grafting PNI-PAM chains leads to densification of the xanthan core. In contrast, the zeta potential distribution was unimodal. Hybrid particles exhibited a very low negative surface charge, around -6 millivolts, much lower than that of xanthan. This is explained by the PNI-PAM shell, which effectively screens the electric double layer of the xanthan core. As a result, even though the hybrids aggregate, their electrostatic properties remain largely unaffected. The particles tend to form labile or loose associates in which they do not overlap strongly and largely preserves their individual structure. Because of this, aggregates show essentially the same zeta potential distribution as individual particles. TEM study gives us interesting more visual evidence of interparticle shell interactions. On this image, we circled a few small areas of high electron density, which seemingly corresponds to hydrogen bonding of amide groups from neighboring shells. Besides, whole particle sizes calculated from TEM correlates to ones obtained with DLS. In conclusion, we successfully synthesized and characterized xanthan PNI-PAM hybrid nanoparticles that display temperature-sensitive behavior in aqueous media. Their combination of structural stability, high water solubility, and tunable thermoresponsiveness makes them promising for applications in smart materials, particularly in biomedical and environmental fields. Finally, I would like to acknowledge my co-authors. Thank you for your attention, and I will be happy to answer your questions.
Thank you for your presentation. Do we have any questions in conference call or probably in Unfortunately, no questions. So thanks once again for your presentation.